the Institute, and he'll tell us about convolutional networks.
And hierarchical tensor decompositions. Okay, hi everyone. Thanks for having me here and for attending. I gave a talk about a month ago which covered more or less the same material, but in a much more applied viewpoint. So how many people here attended that talk? Okay, so it's a minority. For those that are more interested in the practical bottom lines of what I'll be talking about, I will mention them, but the previous talk was more appropriate for that, from that perspective, so I apologize in advance. This is going to be focusing on the theory. How many people here know what convolutional networks are? Okay, so probably about half. And tensor decompositions. How many people here work hierarchical tensor decompositions? Okay, I'll try to fill in the gaps. It's not going to be easy. I'll try to fill in the gaps as we go along. Okay? So this talk, by the way, expressiveness of convolutional networks through hierarchical tensor decompositions. So if you understand convolutional networks and hierarchical tensor decompositions, we're halfway through. Okay, the talk is based on a pretty long series of papers. We're all done in my former group at the Hebrew University with Amnon Shashua and doctoral students Or Sharir and Yoav Levine. Can you see the slides? Is that okay? And master's students Ronen Tamari and Yakira. Okay, so before I start, allow me to spend a few minutes conveying maybe my personal perspective on what it means, the theory of deep learning, and what's the state of this field. And then after a few minutes of babbling and hand waving, I'll start talking about what we actually did. Okay? So, if you want to talk about deep learning, that's a particular case of statistical machine learning. And we will start by laying out the formal setup. Okay? So we have an instance space, X. This is the space of objects that we care about. Okay, so for example, 100 by 100 grayscale images, you could represent them as just matrices of size 100 by 100. Okay? These are the objects that we want to say something about. We have a label space. That's the set of possible labels that we assign to instances. Okay? So it could be continuous if we're interested in measuring some continuous properties of the instances, or it could be discrete or finite if we want to categorize. For example, say if an image is a cat or a dog, the possible labels are just 0 and 1. That's it. There is some distribution over labeled instances. We do not know this distribution, but we assume that it exists. Okay, so arguably it's kind of philosophical, but this is true in general. The world is governed by some distribution that we don't necessarily know. There is some loss function. Okay, this is a function that measures the deviation, the discrepancy between two labels. Okay, so if your labels are continuous, for example, a natural loss could be the square difference. Okay, this tells us how close a particular label is to a different label. Okay, it'll tell us how well we do in our predictions. The task is as following. Given a sample of m pairs, m labeled instances that are drawn IID from the distribution, we would like to return a hypothesis, okay, so-called a predictor. That's a function from instances to labels that minimizes what is called the population loss. Population loss is simply the average over the distribution of the world of the loss that our prediction has with respect to the true label. Okay? Is this all familiar? I know for some it is, but I assume for others it might not be that trivial. Okay, so this is a population loss. This is our goal. Okay? If we put aside all the million details, the fundamental approach of the basic form of statistical learning is the following. We predetermine some set of hypotheses, some set of predictors, and we return the hypothesis that minimizes the empirical loss. What is the empirical loss? This is the average loss over our training set. Okay? This is something that we can actually measure. We can't measure the population loss because we don't have access to the distribution D. But we do have access to the training set. And so the empirical loss is just the average loss over the training examples that were given. Basic approach is pretty much the most straightforward thing that you can think about. Okay? Just return the hypothesis that's best on your training set. Okay? Now there are three fundamental factors that determine how well our final return predictor will do. Okay? This is an illustration of all possible functions from instances to labels. In here you have our hypothesis space. Okay? F star D. This is the ground truth function. This is the function that has the minimal population loss over all possible functions. Okay? It does not depend on us in any way, only on the distribution of the world. It doesn't depend on the hypothesis space that we chose, definitely not on the training set. H star D, this is the hypothesis that has the minimal population loss within our space. Okay? It depends on our space, but it does not depend on the training set. And this is not something that we can find, because we don't have access to the distribution D. Okay? H star S, this is the hypothesis that is optimal on our training set. This is something that we can actually find if you put aside computational issues. Okay? And H bar is what we ultimately return. Okay? Now there are three sources of error. The first is approximation error, also called expressiveness. This is the difference between the ground truth function and the best function within our space. Okay? The larger our hypothesis space is, the smaller this error term will be, obviously. And this has nothing to do with statistics, just a matter of function approximation. The second term is the estimation error, often referred to as generalization, related to overfit and things like that. And this is kind of a statistical error. The fact that we have a predictor that does a good job on the finite training set doesn't mean that it'll necessarily do a good job in the real world. It depends maybe on how many examples we have, right? If we have a lot of examples, at least intuitively, it's clear that the performance on the training set is reflective of the performance of the real world. But in practice, we don't have an infinite training set. So this thing is non-negligible. And the last source of error, that relates to the fact that it's not always easy to find this empirically optimal hypothesis. Oftentimes, these optimization problems are non-convex, and we don't find the best solution. We find an approximation, and this creates a third source of error, which is called the training error. Okay? Now, so some people here that deal with machine learning may start throwing whatever food they give away here on me. But for those that are not, this is my view of how we understand these three factors in classical machine learning versus in deep learning. Okay? So in classical machine learning, it all starts off from the fact that the optimization problems that we face when we minimize the empirical loss are convex. Okay? So we could actually find this empirically optimal hypothesis, and the training error is 0. Okay? And for the expressiveness and generalization, the approximation error and the estimation error, we have the well-known bias variance trade-off, which intuitively means that if you increase the size of your hypothesis space, the approximation error decreases. That is obvious. And what's a little less obvious is that the estimation error increases. You need more examples if you want to learn from a large class of functions. Okay? And the opposite occurs if you shrink the space of functions. Your approximation error increases and your estimation error decreases. And this trade-off manifests itself in many forms in classical machine learning. And I would dare to say that after a few decades of working on these problems, we have a pretty well-developed theory around this. Okay? In deep learning, the situation is very, very different. Okay? In terms of optimization, the empirical loss minimization is a non-convex problem. And there is not just one H star S. There are many of them. This is not unique. And a lot of hypotheses have good training error. And it's not obvious how we can find them. Okay, a priori, this is a non-convex program, but for some miraculous reason, SGD, you could just think of as gradient descent, manages to reach one of these solutions. And we don't really understand why. And with expressiveness and generalization, the situation is even more surprising. Over there, we know for a fact that some low training error hypotheses, some of these H star S's generalize well. They have a low population loss, but others don't. And we know that for typical problems, whatever typical means the problems that we actually run in practice, the solutions that are returned by SGD often generalize well. And we don't understand why. And maybe even more surprising is the fact that when you increase the size of your hypothesis space, obviously the approximation error decreases. But it turns out that the estimation error decreases too. Larger models generalize better, roughly speaking. And we have no idea why this is the case. And it seems like the more expressive your architecture is, your space of hypotheses is, the better the final performance of your predictor is going to be. Okay? And I guess most people would agree, experts or not, that this is something that's not well understood right now. Right? And now, after a few minutes of the promised hand-waving and babbling, I'll start talking about what we actually did. Are there any questions at this point? I assume for some this is what I talked about is trivial, for others maybe not. Okay, we are good? Yeah? I'll assume so unless you say something, so. Okay. Yeah.
So how do you know that it reduces the estimation error if you cannot really find it?
It's just an empirical observation. You have a validation set. Okay? That you have a validation set. The experiment goes like this, for example. I have a training set and a test set. Okay? I run two networks, one smaller and one larger. Each network is a hypothesis space, right? When you change the parameters, it changes the function. Okay? So I train two models. Both reach zero training error, but the larger one has a lower test error. That is a contradiction to what we're used to. We're used to overfitting examples. You know, the fitting a curve to points on a plane, that example? You have them scattered, and if you pass a line, it's better than having a high-degree polynomial.
But I mean, how do you know what is the best solution, HS star?
I know that it's zero. It's very close to zero.
The examples such that?
No, I know that a solution that fits the training data perfectly is always found. We designed the networks to be large enough, so I know that it's the best. But that's a good question. Okay, so that was pretty informal, but now we're going to start being formal. And what we're going to do is we are going to study the expressiveness, which is the first source of error, the approximation error of convolutional networks. And we're going to do this by establishing an equivalence between convolutional networks and hierarchical tensor decompositions. Okay? So the real talk starts now. So, what are convolutional networks? Some may say that it's the most successful thing ever created by man, in general. So, it's by far the most successful deep learning architecture. Okay? AI wouldn't be what it is without convolutional networks. Every type of AI that you encounter that processes images or videos is ultimately based on this. Right? The architecture, roughly speaking, is as follows. You have an input image. Okay? Think of it this as a two-dimensional array. And then I slide a filter across the image to create this heat map, which is called a feature map. I repeat this process multiple times, and I get multiple feature maps. Okay? That's called a convolution operation. Then I take every number here in all of the feature maps and apply some kind of nonlinearity to that. Usually, just take the negatives and clip them to zero. Oh, that's it. Then there is a subsampling layer called a pooling layer. What is done here is that the height and width are shrunk. Okay? You take small windows and you summarize them by a number. This is just some form of subsampling. Okay, so I could have little windows here, and I take the maximum of each window and replace it by a single number here. And so that's pooling. And then the process repeats. Again, convolutions with many filters, pooling, convolution, pooling, until all the spatial dimensions collapse. And then I have a final linear layer at the end. And this miraculous thing is called Linnet. And this is pretty much what spurred the resurgence of AI 5 years ago. The ideas here existed for a very long time, just did it with many training examples and large models, thanks to hardware, essentially.
Who named it Linnet?
It's Jan LeCun.
Himself.
So did he name it after himself? I'll let you kind of be the judge of that. I don't know. I wouldn't rule out entirely the possibility that he named it. But I don't know. OK, so modern networks actually don't look exactly like this. There are different types of variants, different ways to connect layers. We'll talk about some of these variants. But for now, just know that there's an entire zoo of networks. DenseNet, WaveNet, ResNet, GoogleNet. And these are just the most famous ones that won prizes. There are thousands of variants. OK? But in general, convolutional networks, they're kind of the cornerstone of deep learning. OK, so what we're going to do now is construct from the bottom up function spaces, and very naturally, convolutional networks are going to arise. Okay? So we are interested in realizing functions over many local elements. These could be pixels, or audio samples, or text represented as vectors, text words, but just think of them as pixels. Okay? We want to realize functions over many pixels. Let Rs, this is the space of pixels. Right? So if the pixels are color pixels, RGB, then Rs is just R3. Right? Now, consider the space of functions, Hilbert space of functions over a single element. These are functions over a pixel. Right? That's a vector space, a Hilbert space. And also consider the space of functions over a tuple of n elements. Right? This is the space of Rs times itself n times. Okay? Now, it is a well-known fact, I'll explain what this means, that the functions over tuples, the space of functions over tuples is equal to the tensor product of the space of functions over pixels with itself n times. What does this mean? It means the following. If this is a basis, these are functions, this is a basis for the space of functions over pixels, okay, wavelets or whatever kind of basis you want to work with, then the following is a basis for the space of functions over tuples, okay, over images. It's created as follows. I have a tuple of n elements. I apply one of the basis functions to the first, then another one of the basis functions, or maybe the same one, doesn't matter, to the second, then to the third, to the fourth, to the fifth, continue until I finish, and then take the product of the result. So this is a product function that intakes a tuple, returns a scalar. Taking all possible product functions of this form gives me a basis for this. Okay? That's what it means. So if I have a basis for functions over pixels, I can create a basis for functions over images through these products. And this is something well known in tensor analysis. Okay. So in practice, you don't work with infinite dimensional spaces. We limit the dimension. We work in a subspace of the functions over pixels, and we limit the basis to have m elements. Okay? We call these functions descriptors. These are functions that are applied to a pixel, I remind you. And a general function over a tuple can now be written as follows. The same as what we had before, but now we only have m basis elements. So this is a general form of a function. We have a summation over all possible product functions, and these are the linear coefficients. Okay? So if our image has 10,000 pixels, okay, then capital N here is 10,000. And if we decide to describe each pixel with 256 descriptors, then there are 256 to the power of 10,000 possible product functions like this. 10,000 times I choose a number between 1 and 256, apply it to the respective pixel, and then take the product of the result. Okay? So there are many, many functions in this basis, in this product basis. Okay? And I can think of the coefficients as a multidimensional array with 10,000 dimensions and length 256 in each dimension. I call these coefficients, this multidimensional array, the coefficient tensor. Okay? This is the example that I just described. Now, I want to make sure that you all understand this. So please ask questions. And if you don't, I'm just going to repeat what I said in the last 2 minutes. Any questions about this? Not clear what to ask. OK, I have M256 functions. These are functions. They intake a pixel. They return a number. Okay? So these are functions over pixels. Now I create these product functions. Okay? If I had m possible, if I had a basis of size m, and now I lift my function space from a single element to n elements, 10,000, then I do it as follows. I take one of the basis elements, apply it to the first pixel. Then take another one of the basis elements, apply it to the second pixel. Take another one, apply it to the third. Take the product of the results. I get a number. That's a product function, and there are many of those. A general function over images can be written as a linear combination of these product functions. Okay? Are we cool with this? This is just a way, a very, very standard way, there's nothing that we invented here, to take a function space of a single element and extend it to a function space over multiple elements, over tuples. Okay? So actually, if you think about, let's give an example. You have the space of Hilbert, you have the Hilbert space of square integrable functions over R. Okay? Think of a basis for these. All right? And you have the Hilbert space of square integrable functions over R2. Okay? Apparently, if you take the basis functions for R1 and create all the possible products, you get basis functions for R2. Is that clear? Yeah.
But those are infinite bases. When you truncate, you have to...
That's right. So what I said, this applies to the countably infinite case as well. I'm limiting it here to subspaces. It's the same idea. Okay. Think about a finite. Think about about a matrix. Okay. If I have a vector space, okay, and I look at the indicator function, a matrix, you can span vectors. Okay. Think about it this way. I see that this is going a little bit harder than I thought. I have a vector space. Okay. I have a basis for that. It's an m-dimensional vector space. Okay. And I represent these vectors through the standard basis. 1, zeros. 0, 1, zeros. Okay, standard vectors. And if I think of the space of matrices, these are just outer products of the basis elements that I started with for the vector case. Okay? All right, we're going to move on. The bottom line here is that this functional form, if I take m to infinity, I can represent any function this way. Okay? By limiting m to a finite number, I'm just limiting myself to a subspace, and m could be whatever I want. Okay? All right, so up to this point, I didn't do anything unnatural. I just started off with a space of functions over pixels and extended it to a space of functions over images, which is just a tuple of pixels. All right? Now, these functions, these are represented by coefficient tensors, and these coefficient tensors are huge. Okay, if we have an image with 10,000 pixels, we represent every pixel with 256 descriptors. These coefficient tensors have 256 to the power of 10,000 elements. Now, you can't do anything directly with these things, with these objects. Okay? The key observation that we make is the following. If you apply a hierarchical tensor decomposition to these coefficient tensors, you get something that is computed by a convolutional network. Okay? Let's go through this slowly. Hierarchical tensor decomposition, for now, just think about it as a multi-dimensional version of low-rank matrix decomposition. Okay? If I have a million by million matrix, it's very large, it's hard to store in many computers. I can represent it as a product of two matrices, million by 5 times 5 by a million. I've reduced the number of parameters from 10 to the power of 12 to 10 to the power of 7. Obviously, I paid a price. I can't represent anything, but I can still represent very large objects very efficiently. Tensor decompositions, it's the same. You represent high-dimensional arrays very efficiently through such sums and products. Okay? We'll give concrete examples, but for now, that's the idea. So if you apply these high-dimensional SVDs to the coefficient tensor, apparently you get something that is exactly computed by a convolutional network. Okay? It's a specific type of convolutional network. It doesn't have these nonlinearities after the convolution that I talked about. And the pooling, the subsampling, is based on a product operation. So I have windows. I don't take the maximum over a window. I take the product over a window. This is an arithmetic circuit, just sums and products. So we call this a convolutional arithmetic circuit. Okay? And apparently the type of hierarchical decomposition that I use, okay, whatever type means, we'll show examples, that directly determines the structure of the network that computes the function. Okay, so if I change something in the decomposition, something changes in the structure of the network. And the parameters of the decomposition exactly map to the weights of the network. So ultimately, these two things are exactly the same, these hierarchical decompositions and these networks. It's just a different way to look at it. And we'll now show examples, but I want to make sure that the essence of the idea is clear. Okay? We started off with functions over pixels. We extended that in a very standard way, but understand that not all people here are familiar with this. We extended that to functions over images, just tuples of pixels. Then we got this huge coefficient tensor, huge multidimensional array, whose number of axes is the number of pixels in the image. We understood that this is not something that you could work with practically. And then we noticed that if you plug in a hierarchical decomposition, which is a high-dimensional version of SVD, you get something that is exactly computed by a convolutional network.
Does it mean that the low-rank decompositions are equal to what the coordinates are computing, or you mean that you can think of what the coordinates are doing as operating over a tensor and then decomposing?
So it's this. My answer is yes to both questions, but you add a little or there in the middle, so I don't see the difference.
No, so either coordinates express the low-rank tensor.
No, the coordinate computes the function under the decomposition. Okay?
No.
Okay, I have a functional form here. I plug in. I can't compute this directly.
Any function may be.
So any function could be written like this up to that capital M. If I take that capital M to infinity, any function could be written like this.
Right, so M is finite, but still this is interactive.
Okay.
Like a very, very large
Yes,
function.
think about it like this. Any function could be written this way. But you can't represent these huge tensors. So once you plug in a hierarchical decomposition, you give up something. You can only represent a set of possible tensors, like in the low-rank decomposition case. Million by million matrices, if I represent it as million by 5 times 5 by a million, I can't represent anything. Only those matrices of rank 5 or less.
Okay.
So I do give up something. If you plug in a decomposition, so you give up something. You can't represent any tensor efficiently. And what you get is something that's computed by a convolute. This is just an interpretation. This is what convoluts do. We are just interpreting it here. It's not that we're imposing extra constraints. I'm now telling you what a convolute does behind the scene.
But just let's assume that we're talking about matrices. Okay? So
Okay.
you would say that in this case, that the coordinate equal the low-rank matrices?
I would say that the convolute realizes such function under low-rank matrix decomposition, and that 5 is an architectural, translates to an architectural feature of the network. And if I change that 5 to 7, something changes in the network. It becomes a little wider. Okay? Now this is a high-dimensional case. There are a lot of parameters. It's much more complicated, but that's the essence. Okay? Mm-hmm. Are we cool with the general gist of what's going on here? Yeah? Okay. So let's give examples. The most classic tensor decomposition, which I'm sure that many of you know, is called CP. Maybe you know it under a different name. CP decomposition is just a rank 1 decomposition. I can represent a tensor of order 10 as a summation of rank 1 tensors. What is a rank 1 tensor? It's just an adder product between vectors. Okay? Think of matrices. An adder product between 2 vectors, that's a rank 1 matrix, right? An adder product between 3 vectors, that is, by definition, a rank 1 tensor of order 3. I could take this on to whatever order I want. CP decomposition represents tensors as linear combinations of rank 1 elements. Okay? This dates back more than a century ago. Okay? In circuit complexity, right, well, I'm sure you guys encounter these things.
Yeah, there are things.
There are problems that relate to tensor decomposition. Usually order 3, 4 tensors, stuff like, here it's, the order is on the number of pixels. It's much larger. We're dealing with huge tensors, but same decomposition. Apparently, if you plug this in to that functional form, you get something which is computed by this network. This is a convolutional network with a single hidden layer. Okay, you have convolution and then pooling. Everything is decimated at once, and then a linear layer at the end. The number of channels here, the number of filters, is exactly the number of terms here. Okay? The parameters here in blue, these vectors, these weight vectors, are exactly the weights, the linear weights of the network. These two things are the same. It's just a different viewpoint. Yeah, there's a question because I'm going to move.
Non-linearity.
So there is no nonlinearity here.
Oh,
There is product pooling. I will treat how this can be extended to ReLUs and stuff like that. Okay? So far, this is linear. This is a product. That's what's called a convolutional arithmetic circuit. Okay? I'll explain how this can be extended to ReLUs and stuff like that. That's the basic idea. Now, that's maybe the less interesting example. A more interesting one is the following. This decomposition is called hierarchical Tucker. This is the most classic hierarchical decomposition, and it's pretty new. It was introduced in 2009. Let's try and understand how this decomposition works. Okay? Suppose we would like to represent a tensor with 1,024 dimensions. Okay? CP decomposition, what does it do? It takes collections of vectors, 1,024 collections of vectors, constructs rank 1 terms by taking an outer product between 1,024 vectors at a time, and does a linear combination of those. A hierarchical decomposition operates differently. I start off with my vectors, and I construct matrices out of those. Okay, take outer products, linear combinations. These are matrices. Then I take pairs of matrices and construct order 4 tensors. I take an outer product between 2 matrices, I get an order 4 term, and then I take a linear combination of those. And I repeat this, get an order 8 tensor, and then order 16 tensors. Continue in this way. There's kind of a binary tree underlying this process until I get my order 1,024 tensor. That's the idea behind hierarchical tensor decompositions. You incrementally create tensors of increasing order. And that process is governed by a tree. Yeah?
It's the same coordinates involved in all of them.
What do you mean coordinates?
So I mean, you take one with 2, and then you don't take one with 3.
I take one with 2. There are no overlaps. In the classic form, no over. 1 with 2. I have sets. Let's think of a simpler example. I have sets 1, 2, 3, 4, 5, 6, 7, and 8. Each one of these sets, that's a collection of vectors. I take vectors from set number 1 and set number 2, create matrices. Then vectors from set number 3 and 4 create matrices. 5 and 6 create matrices. 7 and 8 create matrices. There's a structure, a tree structure. But the tree could be structured in various ways. It could connect 1 and 2, 5 and 7, 6. It's just a tree.
Linear combinations of them, like 1 and 2 and 5 and 7, and 1 and 2 and 1 and 5 and 2 and 7. Like
no, it's a tree. It's a tree, okay? I have my nodes are 1 through 8, and then I just combine 2 nodes at a time. Okay, but I could take 1 and 2, combine them, and then add 3 to those. It's just a binary. Yeah, you could do that. But there are no overlaps. 1 is combined with 2. It's not going to be combined on its own with something else. Okay, but this is the classic form, hierarchical Tucker, HT, and it's works as I described. Matrices to vectors to matrices, matrices to order 4 tensors to order 8, and so forth. If you take this thing and plug it to the coefficient tensor here, you get a function that is computed by a deep network. Okay, this is similar to what we had before, but instead of a single hidden layer with global pooling that pools everything together, now you have many hidden layers. Each one of them pools over small windows. In fact, each one of them pools over windows of size 2. And that exactly corresponds to the fact that we combine 2 tensors at a time. Okay? So the pooling windows are of size 2. Every stage here in the decomposition corresponds to a hidden layer. The number of terms in a stage is exactly the width, the number of filters in the corresponding layer. The parameters here in blue are exactly the linear weights. These 2 things are exactly the same. Okay?
But again, here, so you don't allow overlaps, like in a general deep network, you do allow overlaps.
That's a great question. The classic form, there are no overlaps. This can be extended to include overlaps, but right now, no, there are networks with no overlaps. Some include overlaps, some don't. But if you want to treat overlaps, you have to consider other variants of this. Classic form, no overlaps. Okay? So, what did we do up to this point? We, in some way, lifted functions over pixels to functions over many pixels. Then we got this kind of functional form with huge tensors, whose number of axes is the number of pixels. That's huge. We plug and we observed that if you plug in tensor decompositions into these coefficient tensors, you get a function that is computed by a convolutional network. And the type of decomposition that you used determines the type of network that you get. And we saw two examples, CP and HD. And we saw in each example how the parameters, the settings of the decomposition translates into architectural parameters in the network. Okay? Now, I was asked about ReLUs and stuff like that. So what we have done up to this point, we established an equivalence between hierarchical tensor decompositions and convolutional arithmetic circuits. Convolutional arithmetic circuits, convecs, they actually work pretty well in practice, but these are not the most standard types of networks people use. Usually people use networks with nonlinearities and max pooling and stuff like that. Without getting into the details, I'll only mention that this equivalence can be extended to other types of convnets, and the way this is done is as follows. In the tensor decompositions, I have a tensor product. Tensor product, that's just an outer product. Two arrays, they're outer product. Okay? Every entry in the outer product is a multiplication of entries from the two arrays. If I replace multiplication by an appropriately defined function g, then I get what is called a generalized tensor product, and then the equivalence holds with other types of convnets. So if I go to the decompositions that I had here and replace these outer products by generalized outer products, for example, ones that take maximum between pairs of entries, I get a generalized decomposition, and that would correspond to a network with nonlinearities and with ReLU and max pooling and whatever you want. Okay? But the natural thing, I guess, are convecs. They are what is born from standard decompositions, and that's what I'm going to be focusing on in the remainder of this talk. Okay?
Nadav,
Yeah.
can you say a bit more about when you say they work pretty well in practice? I mean, it seems like the fact that you don't have nonlinear activation function makes it much milder to analyze. So, do you think it's enough to just focus on this class?
Okay, so
or are we really missing something that is important?
okay, so that's a good question. So first of all, we tackle this in different approaches. One is to implement these things, and there's a version of on Caffe. There's going to be one on TensorFlow soon, and it works the same. The biggest problem is that you can't multiply many numbers in a numerically stable way, right? If you multiply 1,000 numbers, usually it goes to 0 or infinity. So you have to do everything in log space. And then you have logs and exponents, so it runs slower. But it works exactly the same in terms of performance. And so that's one thing. So if you ask me now if that's a critical thing, I think it's not.
So you think if you understand these...
Yes, I do. First of all, I do. And on the theoretical end, we have done works on extending this analysis to ReLUs and stuff like that. Actually, we found out that, at least in terms of expressiveness, they are inferior. They are worse than convecs. Doesn't mean that they work worse, right? They run really fast, and people have done a lot of work on training them. But at least from a formal aspect, in terms of expressiveness, they're provably worse. So right now, if you ask me what I think the reason why these ReLUs work so well is because thousands of people worked on it for many years and tuned it, and yeah.
But if you claim that, can you reconcile that with the situation in normal feed-forward net, where if you without the nonlinearity, you're just...
Okay, so this analysis doesn't capture feed-forward networks. In feed-forward networks, if you don't have nonlinearity, then everything is linear.
Which, yeah,
so obviously there you lose. There it's critical. But these are different models.
It's not.
The conclusions I'm giving for convolutional networks don't transfer to fully connected. These are different things.
You can also implement the equivalent convolutional network without nonlinearity, right? That won't have any of the multiplication issues that you're talking
No, we if they don't have product pooling, they have maximum. Yeah, we have the product. Okay, so what we're going to do now, so we started a little bit late, so can I take this on to 110? Is that okay? All right, cool. Okay, so let's now, once we've established this equivalence, let's start addressing questions on expressiveness. Okay, recall that there are three factors: approximation error, estimation error, optimization error. That's expressiveness, generalization, and training. And we are focusing on expressiveness, which at least empirically seems to be the dominating factor for some unexplained reason. Okay, so we're going to focus on various questions, starting with the efficiency of depth. Okay, it's a long-standing conjecture that deep convolutional networks can realize functions that require shallow networks to have exponential size. This is just a separation argument. Okay? And it's widely believed that this holds in a very strong sense with convnets, because we know empirically that every year, as they get deeper, they seem to work better. Okay? But this is not something that's known. And we are going to prove this through the viewpoint of hierarchical tensor decompositions. We're going to compare tensor decompositions, and then we'll see that this indeed holds. Okay? So let's translate this question to a question on tensors. Okay? Recall this is our functional form. CP decomposition, that's a linear combination of rank 1 terms. The number of terms is exactly the width of the hidden layer in the corresponding network. The corresponding network is a shallow one. HD decomposition, that's this hierarchical decomposition, and that corresponds to a deep network. If we translate the efficiency of depth conjecture to a tensor decomposition viewpoint, we get the following. HT decomposition realizes tensors, coefficient tensors, that require CP decomposition to have exponential rank, okay, an exponential number of terms. Okay? HT decomposition realizes a tensor that's precisely equivalent to some function here. If CP decomposition needs an exponential number of terms to replicate that coefficient tensor, it means that the shallow network needs an exponential number of channels here, of filters, to replicate that function. Okay, so this is just reframing the same question from a tensor viewpoint. And we prove this. We show that not only does HT decomposition realize tensors that require CP decomposition to have exponential rank, but this actually happens almost always. For almost all parameter settings in HT decomposition, you get something that if you try to replicate with CP decomposition, number of terms would have to be exponentially large. Okay, so this is a very, very strong form of separation. Separation happens almost always, and this is something that was not known.
But these are exact results, they're not approximation. What if you want to approximate?
Great question. If you want to approximate, then it's not almost always. There is some probability. Right now, I could state this result as follows. Randomize these weights by any continuous distribution. With probability 1, you get something with an exponential rank. Now you're asking, I don't want to realize exactly that tensor. I want to approximate it. It's not going to be probability 1. That's the answer. It's going to be 1 minus epsilon. But we have results on that too. They're just not as strong. Okay? Still this, by the way, I'll talk about it, but this does not hold for the standard convnets with ReLU and stuff like that. This result doesn't hold. It's weaker. The depth efficiency is weaker there. If we go back to the network viewpoint, translate this result, we get the following. Randomizing the weights of a deep network by continuous distribution with probability 1 gives you functions that if you try to replicate with a shallow network, that shallow network would have to be exponentially large. And so that's a very strong form of separation. It's something that in deep learning there are no alternative results of this form. That not only show that there are results that show separation between deep networks and shallow ones, but not ones that analyze how frequent this property is, and definitely not showing that it happens almost always. Okay? We generalize this result in various ways. For example, we don't only compare the shallow CP and a deep HT, we compare other decompositions in networks. In a nutshell, the price that you have to pay when you cut off layers is double exponential in the number of layers that you cut off. We also extend this to these ReLU networks. We analyze the generalized decompositions, and we show there that there exist functions that deep nets realize and shallow nets can't. But this no longer happens almost always. So with the standard convnet, if you randomize the weights, there is some non-negligible chance that you will get something simple that you could easily do with a shallow net. That's not the case with convex. That's the case with ReLU and max pooling and stuff like that. Okay? So in general, I think it's safe to say that the efficiency of depth through this tensor decomposition viewpoint for convolutional networks is something that we now have. Any question on that efficiency of depth? Okay, let's move on. Now we're going to focus on a different question. The fact that there is depth efficiency, that deep networks can do things that shallow networks can't, doesn't mean that deep networks are worth anything, because maybe these extra capabilities are not relevant to reality. Practice shows us that they are. Deep networks are able to realize amazing things. And there are different questions of why. Why did the functions they realize actually suit the needs that we have for real-world problems? So we focus here on a particular aspect. Recall, convolutional networks realize functions over many elements. And a very important property of such functions are the interactions that are modeled between sets of elements. Okay, so I haven't formalized what interactions means, but at least intuitively it's clear that if we realize functions over images, and we think about the pixels in the blue locations, the set of pixels in blue locations and set of pixels in yellow locations, it seems that they would be highly correlated here and much less correlated here. So we'd like our functions to somehow be able to model strong correlations, strong interactions here, whereas here it might be a little less important. Okay? And so the questions that we ask are, first of all, we need to somehow formalize what interactions mean. Once we've done that, we'd like to know what kind of interactions do convnets model, and how do these interactions depend on the architecture of the network. There are some architectures that seem to work very, very well in practice. Somehow these architectures reflect the needs of real-world problems. We want to have a better understanding of that so we could design networks in a more principled way. Okay? So is this clear, the kind of question that we're asking? Good. What we're going to do now is turn to the world of quantum physics. I assume there aren't many physicists here. I'm not a physicist myself, so definitely won't be too far-fetched. We're going to use concepts and tools from quantum physics, first of all, to formalize what interactions means, and then to analyze their behavior. Okay? So let's try and explain. We have a set of n particles. Okay? These are quantum particles. Okay? In quantum physics, the way physicists model the state of a particle is through a vector in a Hilbert space. I assume at least some people here know these things. In quantum physics, they model a state of an object as a vector in a Hilbert space. Okay, so this is just a linear combination of basis functions. And a state of a system of n particles is modeled as a vector in the tensor product space. Okay, so this is a linear combination of these tensor product bases. And they have a coefficient tensor, just like we do in the convex C derivation. Okay? And quantum entanglement measures are concepts that physicists defined to quantify interactions between particles in a quantum system. They care a lot about interactions between particles. It has very deep implications. There's an entire field called quantum entanglement that deals with this. What we're going to do is adopt definitions and tools and use that to characterize entanglement between pixels. Okay? All right, so this is a system state. That's a state of n particles. Let's consider a partition of these particles to two groups somehow. This is the set I, set of particles, and this is its complement. Okay? What physicists look at is the matricization of this coefficient tensor according to I. This is just taking the tensor and arranging it as a matrix where rows correspond to particles indexed by I and columns correspond to particles indexed by the complement. Okay, so in NumPy or MATLAB, you have a high dimensional tensor. You rearrange the dimensions so that those of I come first. Here it's already the case. And then you just reshape it as a matrix. Okay? Why do they do this? Because that is how you can measure entanglement. Let sigma be the singular values of this matricization. Entanglement between particles of the particles of I and those of the complement are defined based on the singular values. So there are different definitions, different measures. The most famous one, the most common one is entanglement entropy. That's the entropy of the singular values when they are squared singular values when they are normalized. Okay? So if the spectral energy is focused on a small number of singular values, this is going to be small. If it's kind of spread, this is going to be higher. That's the entanglement entropy. Another measure that people use is a geometric measure. Here, this kind of measures the energy in the second to last singular values. So if everything is focused on the first, or if a lot's focused on the first, this is going to be low. If not that much is focused on the first singular value, this is going to be higher. And the measure that we will work with is called the Schmidt number. That's just the number of non-singular values. That's just the rank of the matrix. So apparently, if I take the state of n particles, look at the coefficient tensor, arrange it as a matrix according to some partition, the rank is going to tell me how strongly the particles from the two sets interact with each other. Okay? That's what happens in quantum entanglement. Now, how's this relevant to us? Notice that there is a very strong resemblance between the structure of a system state that models many particles and a function realized by a convex C. That's just a function over pixels. Okay, look at these two forms. They're essentially in some sense the same. Okay, here you have tensor product bases, here these are product functions. And what we do is we simply quantify interactions that a convex C models between pixels by adopting quantum entanglement measures and applying them to the coefficient tensor here. Okay? Then you get measures for interactions that the function models between sets of pixels. Okay? So I think this is kind of the most, I think it's the most elegant way to present these measures, these entanglement measures. You could look at things differently without quantum physics at all and understand why they make sense. But I think this is the nicest path to go through. So we went through quantum entanglement. But now at the end of the day, how do we measure interactions between one set of pixels and another? Take the coefficient tensor, arrange it as a matrix accordingly, look at the rank. Okay?
So large rank means?
Large rank means high entanglement. Large means high interactions. I could explain this without quantum physics at all, but I think this is nicer in some sense. Okay, so in quantum physics, how do they simulate these system states? They also have very large tensors. They do this through something called tensor networks. These tensor networks are not to be confused with the hierarchical tensor decompositions that we talked about. They're related, but forget about them for a while. These tensor networks are just graphs where vertices correspond to tensors and edges correspond to modes. So a scalar is just a vertex with no edges. A vector is a vertex with one edge. Matrix a vertex with two edges. It's a vertex with three edges. That's an order 3 tensor. And an edge that connects two vertices, that represents contraction. Okay, so if they have a vertex and a single edge connecting them, that's an inner product between vectors. That's how they visualize it. This is matrix multiplication. This on its own is a matrix. This is a matrix. There's an edge connecting, then that means that there's contraction. So it's matrix multiplication. And each edge is weighted by the corresponding dimension. Okay, so if this is a 5 by 4 matrix, this is a 4 by 6, then this edge has weight 5, this edge has weight 4, this edge has weight 6. Okay? It's kind of an intro to tensor networks. Now, what do we do with this? Apparently, the coefficient tensors that are generated by a convex C can be thought of as a tensor network. This convex C realizes some function by decomposing a coefficient tensor. We can represent that decomposition as a tensor network. Okay, and in this tensor network, we have these open nodes here, which exactly correspond to the input pixels. And edges are weighted by numbers that are exactly the widths of the hidden layers in the network. And the structure of the tree, the structure of this graph, is determined by the pooling geometry in the network. Okay, so I'm not proving this, but I'm telling you that these networks realize hierarchical decompositions that can be thought of as these particular tensor networks. Okay? Why is that important to us? Because we prove the following result. I'll say this at least 3 times in this slide, so if you don't catch me the first or second, then we're fine. The maximal Schmidt entanglement that a convex C models between two sets of inputs is equal to the minimal cut in the respective tensor network between the sets of nodes, the corresponding sets of nodes. Let's repeat that in a different way. We have a convex C realized as a function over many pixels. We think of a partition of the pixels to two groups. We ask, what is the entanglement that the network models between these two groups? The answer is, go to the respective tensor network, look at the induced partition. Remember, every node here corresponds to some pixel. Look at the induced partition and measure the minimal cut that separates them. That minimal cut is exactly the entanglement. So now we can quantify interactions and entanglement between pixels as minimal cuts in a graph. Okay? And this means that we can control the interactions, the entanglement that are modeled by a convex C by controlling minimal cuts in some graph. What can we do to control minimal cuts in this graph? We can do two things. Play with the weights, which are the layer widths in a convex C, and play with the structure of the graph. That's the pooling geometry. Okay? So now we have a way to change the architecture of the network so that we maximize the interactions that we care about. Okay? Now I'll show examples with experiments of how we do this. Okay? So with layer widths, what we show is that so these are kind of practical bottom lines. So for those that are interested more in that and fell asleep when I was talking about tensors, this is the moment to wake up. So what we show using this methodology is that the width of hidden layers that are deeper, the ones that are farther down the network, these are important for modeling interactions between pixels that are far away from each other. And on the other hand, the width in early layers, those that come first, that's important for modeling interactions between pixels that are nearby. And we actually demonstrate this empirically. What we show is that when you classify images with large objects, it's more important that your deeper layers be wider. And if you're classifying small objects, it's more important that your early layers be wider. Okay, so this we demonstrate. And in terms of pooling geometry, what we show is that elements that are pooled together early have stronger interaction. The network can model stronger interaction for those. So if you want to model interactions between pixels that are nearby, for example, identify holes and things like that, you should use these type of two pooling geometries. Just combine contiguous elements. That's the standard. On the other hand, if you want to measure symmetry or things like that, then you need to model interactions between pixels that are far apart. And then you're better off pooling together reflections and stuff like that. And we also demonstrate that empirically. Okay? So, heading on to the last question. I'll finish in like 5 minutes. This is the third question. And it relates to interconnectivity. So as I said, this is the Linnet structure that everyone knows, classic one. But nowadays, modern networks look differently. They connect their layers in various ways. It's not just each layer connects to its successor. You have splits and merge and skip connections. What we ask here is whether these connectivities can lead to more efficient representation of functions. Okay, we want to be able to show this. And we again, as always, in the best of tradition, do this by looking at the tensor decompositions. Okay? So the analysis focuses here on convnets on 1D data. This is just for marketing reasons. It's because it's very trendy. These are called dilated convnets. Everything that you use on your phone and it's related to audio, for example, when you talk to Google or Siri, it's based on these convnets. Convnets that operate on 1D data. Okay? And they don't have pooling. Their filters have these gaps. This is something that's super trendy. So we decided to go with the flow and analyze them. And what we show is that with a dilated convnet, this is a dilated convnet, underlying it is some tensor decomposition. Okay, that tensor decomposition follows a tree structure like we talked about. Apparently, if I modify the tree, change the connections, and then return to the network, I get a network with different dilations. Okay? And what we do is we define the concept of a mixed tensor decomposition. If you have two trees over tensor axes, you can combine them by having a decomposition that implements them both in parallel and exchanges tensors between the two trees along the way. I'm hand waving, but that's the idea behind a mixed tensor decomposition. And apparently a mixed tensor decomposition, if you look at it from a network perspective, it's exactly equivalent to an interconnected network. Okay? I had a decomposition with some tree, T. That decomposition corresponded to a network. Then I had a decomposition with a tree T-bar. That corresponded to a different network. The mixed decomposition, blending together these two trees, corresponds to a network that blends the original networks by interconnections between their layers. And so now I have a way to analyze interconnected networks. And what we show is that a mixed tensor decomposition realizes tensors that require the individual decompositions to be much larger, quadratically larger, which in a large-scale setting is infinite. Looking at it from the network perspective, it means that a mixed network with interconnections can realize functions that require the individual networks to be much larger. We demonstrate this empirically also. The bottom line here is that we've shown that interconnectivity can indeed lead to more efficient representation. Okay, so let's now conclude. So we started with the hand waving about statistical learning. At least in my view, it all boils down to these three aspects: expressiveness, generalization, and optimization. If you understand them, then you understand statistical learning in its most basic form. We have a pretty well understanding for classical ML, but very limited for deep learning. For some reason, expressiveness seems to be something very important practically, does not harm the generalization. We established an equivalence between convnets and hierarchical tensor decompositions, whether it be conv-Cs and standard decompositions or convnets with ReLU and generalized decompositions. And we use this to analyze the expressiveness of convnets. Okay, we talked about efficiency of depth, modeling interactions, and interconnectivity schemes. And I think that importantly, these kind of analyses and results, and in general, I think theory of deep learning, it's not just about satisfying our scientific curiosity. It's about making things work better. Because now, and making the process of design, of using these technologies more scientific and more principled. Right now, things are extremely heuristic. There are no principles at all. It's only trial and error and past experience and intuition. And I believe that developing theory behind these models can ultimately lead to them working better. We saw examples here in the case of the interactions, for example, showing you how you should arrange width of layers and geometry of pooling windows, but these are just two small examples out of a whole sea of heuristics. So I encourage you all the theoreticians here, to try and focus on these problems, because they're not only interesting, they can actually make AI work better. And what I'm doing now is trying to use the equivalence to study the next two factors, not just expressiveness, but also generalization and optimization. So whoever is interested in that can come talk to me afterwards. So at this point, I'll stop. Thanks.